everyone. Welcome to Yebo Physics on a Thursday afternoon. I hope I find you well. I can see I've got some company on Teams there. How are you, Miss Punzima?
I'm good, sir. How are you?
I'm doing fine. Thank you for joining. In this tutorial, we're going to be looking at questions that involves electromagnetic induction. And this is the second session. In case you've missed the previous session, please make sure you check on the Yebo Physics YouTube channel. So let's get started. So if you've got any question, as we are solving, please feel free to interject me and pose your comment, question, or contribution. Just to confirm, are you able to see the screen that I'm sharing?
Yes, sir, I can see.
Okay, great. So this question that we have, which is question 8, reads, a horizontal metal rod lying in an east-west direction is moved northward at a constant velocity through the magnetic field that points straight downwards, negative z-axis. See diagram below. Which statement is true? Okay, so amongst the statements that are there, lost my screen there. Okay, it's back. I just want to scroll down to so amongst the statements that are there, we've got 5 statements. No magnetic induction can be induced on the rod. The bottom surface of the rod is at a higher potential than the top surface, that's B. The west end of the rod is at a higher potential than the east. The east end of the rod is at a higher potential than the west end. Then E, the top surface of the rod is at a higher potential than the bottom surface. So one thing that we could agree on is whether we're going to have an electromagnetic induction or not. So first and foremost, we can see that that rod, it's a metal conductor, and it is lying perpendicular to the magnetic field. So as it is lying perpendicular to the magnetic field, so I'm just going to put the representation here. This is the rod, and you've got your magnetic field, which is into the page. So when the conductor is stationary, there's no electromagnetic induction. But the moment that conductor is moved perpendicular to the magnetic field, we do induce an EMF or induce a current. Okay, do we agree on that one?
Yes, sir.
Right. So if we agree, which means that item A is out already. Okay, if we agree that an EMF is going to be induced, therefore we've got a magnetic induction on the rod, then it means that A is out. But what we now have to establish is which side would have a higher potential than the other, right? So to know that, we would have to first identify the direction of flow of current. Okay, we have to identify the direction of flow of current. So we've got our F in that direction, which is perpendicular to the magnetic field, which means that that conductor is going to cut across the magnetic field. So this is your B. So we want to establish the direction of flow of current. So I prefer to use the Fleming's right-hand rule, okay, where the thumb represents the direction of the force, and the first finger represents the direction of the magnetic field, which will be directed into the page or into the board or into the screen. Then the thumb is representing the direction of the force, which is pointing northward in the upward direction. All right. So in this setup, if you use your Fleming's right-hand rule, you establish that your current will flow towards the left. Okay. The induced current will flow towards the left. So your induced current I in the conductor, let me use this marker. Current will flow. So I flows to the west. So current flows towards the to the left. So we know that the directional flow of current follows the movement of positive charges. So this implies that the electrons will be drifting in an opposite direction. Remember, electrons oppose the direction of flow of conventional current. So, which means the electrons drift towards the east. Okay, I went vice versa. Towards the right, which is at the east. So if the electrons are moving towards the east, and electrons, we know that they are repelled by a negative potential. So if the electrons are moving towards the right, it means on this end of the rod, we have got a negative charge, a potential, and on this side, we have got a positive potential. Okay. So what then that means is that at the higher potential is at the right side, okay, which is the east side. So the east side has got a higher potential than at the west end. So that is how you would answer this question. I'm not sure if you got that one.
I got it, sir.
All right. So I'm glad that you're following. So let's move on to the next part of the question. Next question, actually. So question 9. Question 9 reads, a bar magnet is held in a vertical orientation above a loop of wire that lies in the horizontal plane as shown. The south end of the magnet is towards the loop. After the magnet is dropped, what is the true of the induced current? I guess that should be what is the direction of the induced current in the loop as viewed from above. I discuss thoroughly. Okay. So we need to discuss that thoroughly and see what would happen. So I'm just going to try and reproduce that sketch there. So you can also be reading through to see if you follow the question. Okay, so there we are. So this permanent magnet, it has got a magnetic field around it. That's obvious. So as the magnet is moving or falling towards the circular loop, we should ask ourselves what is happening to the magnetic flux in the loop. Is it going to be increasing or decreasing? As that magnet is falling towards the loop, as that magnet is falling towards the loop, is the magnetic flux in the loop going to be increasing or decreasing?
I think so. It's going to decrease.
You think it's going to decrease? So this magnet, okay, listen carefully. This magnet has got a magnetic field around it, right? And as it is moving closer to the loop, the magnetic flux in the loop is going to increase because it has moved closer to the loop, because it has moved closer to the loop. So the magnetic flux initially, because the magnet was further away, the flux in the loop was less. But as the magnet comes towards the circular loop, the magnetic flux in the loop is going to increase because the magnet has come closer to the circular loop. Did you get it?
Yes, sir.
So which means the flux has increased from a lower value when the magnet was at the top to a point where it's maximum when the magnet is now in or just closer to the loop. So the flux has increased. And remember, for a current to be induced in that circular loop, there has to be a change in magnetic flux. So we can confirm that as that magnet falls towards the loop, there is going to be a current that is going to be induced in that circular loop. Why? Because there is a change in magnetic flux as the magnet falls from a higher position going towards or through the loop. So if you recall this equation, perhaps from class, EMF induced is equals to N d phi over dt, which is d phi, which is the flux. So as long as the magnetic flux changes, then we induce a current. That's according to Faraday's law. Okay. Now, the question requires us to discuss or to identify or to determine the direction of the induced current in that loop. So first and foremost, let's identify the direction of the magnetic field due to the bar magnet. Okay, and we know that the magnetic field is always pointing towards the north. So which means that B, the original magnetic field, will be pointing upwards. Okay, now as this loop falls into the magnetic into the loop, there is going to be an induced magnetic field. Okay, an induced magnetic field, and according to Lenz's law, whenever the flux is increasing, the induced magnetic field is going to be in the opposite of the original magnetic field. So when the flux is increasing, like we noticed, because the magnet is falling towards the loop, so when the flux is increasing, it means that the induced magnetic field will be in an opposite direction. So which means that the induced magnetic field will be going downwards. So the induced magnetic field in the loop will be going. So I'm saying BI because B induced, okay? So now we use the induced magnetic field to determine the direction of flow of current. Now this is where we use our right hand grip rule or thumb rule. So our magnetic field now, we can see it's going down. Since our magnetic field is going down, our four fingers, now this is quite difficult to illustrate, but we're saying that B induced is inside the magnetic, inside the circular loop. If you grip the circular loop on one position, if you grip it here with your hand, you will see that your thumb will point in this direction. So if you grip at this point, okay, if you grip at this point with your four fingers inside the circular loop, because you have to grip in such a way that you are holding the circular loop. So the pen is my loop in this case. So you see that the thumb will point in a clockwise direction. So which means the direction of the induced current will be in a clockwise direction. So basically that is how you would identify the true direction of the induced current. So the summary of the question number 1, as the magnet is falling towards the loop, check what is happening to the magnetic flux. The magnetic flux is going to be increasing. Okay? And if the magnetic flux is increasing, according to Lenz's law, the induced magnetic field in the loop will be in an opposite direction. Now you use the direction of the induced magnetic field to determine the direction of the induced current using your right hand grip rule, where your four fingers point in the direction of the magnetic field and make sure that you are gripping the conductor. So your four fingers are indicating the direction of flow of current inside the loop, and your thumb will self-align in the direction of the induced current. I'm not sure if I explained that in a way that you understand it.
Yes, I can.
You did understand, are you sure?
The kind of part that is kind of confusing is a lot of the clockwise, the gripping of the loop.
Okay. The gripping. So it's a bit difficult to show it here, but I'm going to try. So the gripping, make sure you're using your right hand. I don't know what I can use to illustrate this. Can you see this circular thing that I've made? So the gripping, we're saying our magnetic field is going into or inside, right? Inside the loop. So if you are gripping, you have to hold it in such a way that your palm is in contact with that circular ring, then your thumb will self-align with the direction of the flow of current. So you have to hold your right hand in such a way that your palm grips the conductor and your forefingers are pointing downwards and they are inside the loop. So it's something that you should try to visualize. So your forefingers are gripping the conductor, your forefingers are inside the loop, and your thumb will self-align in the direction of the induced current. So you will see that your thumb will point in a clockwise direction. So I'd say it counterclockwise, it's actually clockwise. So it's in a clockwise direction. Someone has got their mic unmuted. Please mute your mic. All right, so we can also now look at what would happen if, so here we've established that our answer is going to be clockwise. Now let's consider a scenario that it's not a scenario in the question, but we just want to visualize this. Let's say that magnet continues to fall down. If that magnet continues to fall down, this is our circular loop, and you still have got your magnet still falling, going down, and this is your north, and this is your south. So our magnetic field will be in that direction, still upwards. But now that the magnet is moving away from the loop, magnetic flux decreases. Okay, so our flux is decreasing. So this is a scenario when the magnet has passed through the loop and it's now moving away from the circular ring. So the flux is now decreasing. Now, if flux is decreasing, if the flux is decreasing, the direction of the induced magnetic flux will be in a direction same as the original magnetic field, according to Lenz's law. So which means that our flux induced in the coil, which is Bi, magnetic flux induced, is going to be in the same direction as the original magnetic field. All right. Again, you do the same thing. You grip your coil such a way that your palm is in contact with the conductor, and your forefingers are pointing upwards in the direction of the induced magnetic field, and your thumb will be pointing in the direction of flow of current. And we realize that in this case, the direction of flow of current will now be counterclockwise. So it will now be counterclockwise. The direction of flow of current will be counterclockwise. So our current would be counterclockwise or anti-clockwise, right? So that is how you would determine the direction of flow of current in a conductor. So first we did identify the direction of flow of current when that bar magnet is falling towards the loop. So when it is falling towards the loop, you realize that the flux is increasing. So flux in the coil is increasing because the magnet is moving towards the coil. And if the flux is increasing, it means that the induced magnetic field inside the coil, according to Lenz's law, it's going to be opposing the original magnetic field, which is initially pointing upwards, as shown there. Then using your direction of the induced magnetic field, you can determine the direction of flow of current using your right-hand grip rule. We said you have to grip the conductor, make sure that the metal conductor is in contact with your palm, and your four fingers are pointing in the direction of the induced magnetic field, which is inside the coil. And you will see that your thumb or your thumb will self-align in the direction of flow of current, which is clockwise. Okay. Now, when the magnet has fallen through and it's now moving away from the magnet, away from the loop rather, the original magnetic field is still in the same direction, still pointing upwards. But the induced magnetic field now is going to be in an opposite, is going to be in the same direction as the original magnetic field. Why? Because in this case, the flux is decreasing due to the magnet moving away from the conductor or from the loop. So again, you use your direction of your induced magnetic field to determine the direction of the induced current. Then you'll realize that it will self-align in a counterclockwise direction. Okay, so I think this question is answered. Then we can move on to the next question. Okay, so there is the question. Question 10. You can read through. Starting outside the region with a magnetic field, a single square coil of wire moves across the region with a uniform. I'll read that again. Starting outside the region with a magnetic field, a single square coil of wire moves across the region with a uniform magnetic field B perpendicular to the page. The loop moves at a constant velocity as seen from above, so it's below. A counterclockwise EMF is regarded as positive. In which direction did the loop move over the plane of the page? Okay. So we've got several responses that are there. The first one, the loop moved from bottom to top. The loop moved from top to bottom. The loop moved from left to right. The loop moved from right to left. All of these directions of motion will produce a graph of EMF versus T. So this is the graph. Okay. So remember, we said EMF to be induced, E is equals to negative N d phi over dt. So we're saying EMF E is equals to change in flux over the time. That is essentially what that equation says. So which means that whenever flux is changing, an EMF will be induced. Okay? Whenever flux is changing, EMF is induced. Then this is a sketch that we are given. So when this box is entirely outside, so when this box is entirely outside of the magnetic field, we do not expect any induced we do not expect any induced EMF, right? Because it's completely outside. So if we're going to draw our corresponding graph, so this position 1 is this same position 1 that we have here, where there is no EMF induced, right? But the moment this box moves inside, the flux is going to change, right? The flux is going to change, and as it is changing, the flux is actually going to be increasing, right? So the change in flux, remember, for EMF to be induced, we said there has to be a change in flux. So from position 1 to position 2, the flux at 1 was actually 0. The flux at 1 was actually 0. Then at 2, as that coil begins to move into the magnetic field, the flux increases. Okay? So which means that the flux is going to be increasing. Then according to Lenz's law, that is why we have got a negative EMF induced. Okay? Then at position 3, we now have this coil completely inside. Now, when it is completely inside at position 3 now, the flux at this point and at this point is the same. So the flux there is the same. It's constant. Okay? So when it is moving inside the magnetic field, the flux is constant. That is why at this position, which is position number 3, the EMF induced there is 0. Okay? Now, at the instant the rectangular coil begins to move out, it means that the flux is going to decrease because it was maximum at a constant value, which is at 3. Now it's moving from 3 to position 4. So the flux is decreasing. So the flux is decreasing. Since it's decreasing, it's going to be negative gradient. Then with the negative on the equation, it becomes positive. So that is why we have got this type of a graph. All right. That is at position 4. And when the rectangular loop is completely outside, we now have no EMF induced. Okay, this is a graph of T versus our EMF. So at position 5, we no longer have any EMF induced because the flux is 0. Okay, so which explains why we have got that type of graph. All right, and this scenario is true when moving from the left to the right, or from right to left, or from top to bottom, or from bottom to top. So this scenario will still be the same. Okay, that is why you've got those options that are there. So which means that the best option there is all of the above. It's all of the above, because in any of these directions you will still initially have no flux. Flux increases, remains constant. Then when the coil is moving out, the flux decreases. Okay, so whether you're moving from left to right or right to left, top to bottom or bottom to top, the scenario will still be the same. I don't know if you are following this, Mr. Prince Nkambule. Are you following what we are discussing?
I will catch up, Sam. I'm still trying to understand.
Oh, which part are you still trying to understand? Is it on this particular question?
Yeah, is this question, because I don't understand anything actually, because when I look at this thing, the magnetic field is into the page and this component is moving to the right. When you use your left hand rule, isn't the force in the right direction? Or maybe I'm with this today's topic.
Okay, so we are not pursuing, if you look at the options that were given in the question, we are not pursuing the direction of flow of current in the rectangular coil. If you look at the graph that were given there, that graph is trying to explain to us the direction of the induced EMF, number one, and also showing us at which points or positions on that rectangular coil will the EMF be induced. So if you see my sketch that I've put here, where I've indicated position number 1, I want you to, can you see where I've highlighted position number 1? I want you to go with me.
Okay.
So here I'm assuming that that rectangular coil is still outside. Okay. And if that rectangular coil is still outside, do we expect to induce an EMF in that coil? That's my question. No. Look at my graph there. That's where I've got our position number 1 there. We have no induced EMF at that particular position. Why? Because we are saying for EMF to be induced, look at the two equations that I've put. For EMF to be induced, there has to be a change in magnetic flux linkage. When that coil is outside, there is no change in magnetic flux linkage. Therefore, we don't expect any EMF. Let's move. We're pushing this coil towards the right, and you see that one side enters the coil as we are pushing. The other side is still outside. So when the other side enters, it means that the flux now has increased, because we started from a phi of 0 at this position number 1. But as we are moving to position 2, flux is increasing from 0.
Okay.
Are we together at that point? So if the flux is increasing, don't we have a changing in flux or a changing flux?
We do.
We do. That's why you see on my graph there, I have put to indicate that because the flux has increased, so the change in flux is positive because it's increasing. But because of the equation,
Yes.
the direction of, according to Lenz's law, because of the negative there, that's why we see the EMF is on the negative side.
Okay. Yeah, I can see that.
Right? Then we continue to push this rectangular coil until it is entirely in the magnetic field. So now the front side and the back side are inside a uniform magnetic field. The flux at this point and the flux at that point is the same. So are we going to have a change in magnetic flux between the two sides, between the 2 points?
No.
Which means that the flux, the change in flux is 0. So the flux is not 0, but the change in flux is 0. So if the change in flux is 0, it means that there is no EMF. That's section number 3, which is a gap there. There's no EMF induced. We continue to push that rectangular coil. Now it's falling out or moving out of the magnetic flux. So the flux there is now decreasing. It was at a maximum. Now it's decreasing. It is moving out of the magnetic field, which is position number 4. So the flux is going to be decreasing. So its flux is negative. And if we put our equation there, it EMF induced becomes positive. And if we push it further out, now the flux is 0, which is position number 5, which I've put there. So that's all this question. That's all this, what this question is all about. Then they are now asking you which option is appropriate to produce that type of a graph. That's where I was explaining that it's irregardless of any direction that you come from, whether you're coming from left to right like what we did, or even if you want to move from 5 to 1, which is from right to left, you still have the same graph, or even from top to bottom or from bottom to top, you still have a similar graph. So that's why we've ticked all of the above from our options.
Yeah, yes. Thank you.
Okay, all right. So let's proceed to question 11. All right, now this one is the fundamental question that also requires some diligence in terms of working or determining the direction and everything. So we're going to go through it together. So the question says, suppose that when the switch is closed, the current in the left hand loop takes 1 microsecond to build to its steady state value, and that during this time the magnetic flux through the right hand loop increases steadily from 0 to 100 times 10 to the negative 8 Webers. The number of turns on the right coil is 6. Okay, so let's get to the question now. Assume that the switch is just closed. What is the direction of the magnetic field produced by the current at X? Notice that point X, the current carrying wire is under the bar. So can you see point X? I hope you can see point X there.
Yes, can you repeat your question?
So I'm showing the question now. Can you see it? It says we should, at point X, can you see point X? What would be the direction of the magnetic field produced by the current? We want to know the direction of the magnetic field at point X.
it's out of the page.
No, here you need to give it in terms of
Be into the page, if I'm not lost, because the current, we'll be looking at the current traveling from uh the let's say right to left, going down, and when at point X the current will be moving up. So when you use the right hand grip rule, your
yes, I
fingers
get
will
you.
curl.
So in class, have you looked at determining the direction of the magnetic field due to a solenoid?
I don't think so. I'm not sure.
Where you are basically using your right hand grip rule to you're not sure.
Yes, I'm not.
All right, so can you see the direction of current that I've shown there? From the circuit, can you see that current will flow from positive to negative, and this is how the current will flow on that loop to be like this. It goes under like that.
No, sir, can you?
Like that.
I still see the previous. I still see the previous workings. I still see question 10.
Oh, okay. All right. How about now?
No, your screen just got. Oh, okay, yeah, I can, yeah.
So if you look at the question, do you agree that this is the correct direction of flow of current that I've
Yes, sir.
because you have got your positive there and your negative there. So that will be your direction of flow of current. So what would be the direction of the magnetic field at X there? What were you saying? You were trying to answer. At point X there.
So I don't know for a solenoid. Yeah, now it seems confusing because at point X, it's for that metal thing in between. So I don't know how you find you get that.
So there are two ways of doing it. You can use your right hand grip rule where your four fingers are pointing in the direction of flow of current. You grip the solenoid, which is this pen, grip it like this, and your thumb will point towards the direction of the magnetic field. It is from left to right. You can try that and see if you are winning. So your four fingers are gripping the solenoid, and the direction is downwards. So your four fingers should point downwards. And then your thumb will point towards the right.
So, sir, when you curl your fingers on the, does it have to be in your fingers? Do they have to curl in the direction of the current?
They have to curl in the direction of current as shown in the diagram. Yes.
If that's so, that means our magnetic field will be going from left to right, or in
Yes.
the positive axis.
Yes. So it's going to be left to right. Yes, that's correct. So that's how you would work it out. Okay. Now, let's move on to the next one. I'm just going to select the... Then it says, just right after the switch is closed, what is the direction of the induced magnetic field in the right coil? So right after the switch is closed, what is the direction of the induced magnetic field in the right coil? So let's look at the diagram. We want to know what will be the direction of the induced magnetic field. So first and foremost, we're saying this is our original magnetic field. And here we've got a coil. That is going like this. And this is your A, and this is your B. If you want to try, what will be the direction of your magnetic field induced in the coil on the right? So I've drawn the coil on the right there. What will be the direction of the induced magnetic field in that coil?
So I'm thinking of two things now.
Yeah.
It's either we can use the same right-hand rule for the first solenoid, or maybe we'll use how poles are induced between the solenoids and use it that way.
Okay.
I'm not sure which.
Okay, I get you. So I'll ask you a question first. Are we going to induce a magnetic field in that coil? That's the first thing that we should ask ourselves. Are we going to induce a magnetic field? Will there be an induced magnetic field in the coil in the right? From what you have learned.
If there'll be an induced current in the solenoid, then yes, there will be an induced magnetic field. Yes.
So ask yourself, what is it that causes an induced magnetic field? So remember that whenever we have a change in magnetic field, we induce a current. Whenever we have got a changing flux, we will induce a current in the coil on the right. And remember, flux phi is equals to BA. You remember that, right? Now, when the circuit is closed, well, listen, I want you to listen to this carefully. When the circuit is closed, what happens to the magnetic field? This original magnetic field, it increases from 0. So initially, when the circuit is open, we can agree that this B naught is 0. Do we agree? When the switch is open?
Yes, sir.
B naught is 0, which means that the flux is 0. Okay? Now, when the circuit is completed, the current in the circuit will increase from 0 to a certain value until it's constant. And remember, across or every current carrying conductor has a magnetic field. So which means that the instant when the switch is closed, current increases from 0 to a certain value, which means that the value of B also increases from a 0 to a certain value, which means that our flux here is going to increase, because initially the flux was 0, the switch is closed, current flows from 0 to a maximum, which means that the flux also increases from 0 to a maximum. So yes, we're going to induce an EMF in the coil on the right because the flux changed from 0 to a maximum. Do you get that?
Yes, so because of that induced EMF, there will also be an induced current. And starting from the increasing magnetic field, actually,
Yes.
that induced current will be in the opposite direction because of that increasing magnetic field.
All right. So according to Lenz's law, from the question we did earlier on, I think you joined when we're doing that question, where we're saying that when magnetic flux is increasing, when the original magnetic flux is increasing, the induced magnetic flux is going to be acting in an opposite direction. That's according to Lenz's law. So we agree that our B naught was increasing, which means that the B induced is going to be in an opposite direction. So which means that it's going to be from right to left. That's the direction of the induced magnetic field. So the first thing was to identify whether a flux, original flux, is increasing or is decreasing. And because the switch is being closed, which means that the current is increasing, therefore the induced magnetic field is also going, not the induced, the original magnetic field is going to be increasing. Therefore, the induced magnetic field in the coil on the right is going to be opposing the direction of the original magnetic field. That's according to Lenz's law. So right to left. Are you okay with that?
Yes, sir.
Now, the third part, during this time when the switch is closed, what is the polarity of terminal A on the right coil? Positive or negative? Notice that the winding copper wire is going to terminal B is on top. Okay, that's just a hint. All right, let's look at the question. Okay, now we want to find the terminal A. Is it going to be positive or negative? So now we have identified the direction of the induced magnetic field, and we see that it is from right to left, which is our BI. Okay, so now since we now have the direction of the magnetic field, we now use it to determine the direction of flow of current on the right loop. Again, you can use your right hand grip rule. Okay, so now how do you grip? You grip in such a way that your thumb is pointing in the direction of the magnetic field, which is to the left, because we said from right to left. So which means your thumb should point to the left, and you should grip in such a way that your thumb remains pointing to the left, and you grip such a way that your palm is in contact with that coil. So if you do so correctly, you'll realize that your current should be upward like that. Like that. Okay? Which means that our current is flowing towards B. Okay? Do you agree? Do you agree that our current flows towards B? Please let me know if you're still there.
Yeah, yes, I agree.
Current flows towards B. But then how do we determine whether A is positive or A is negative? Now, we know that what we've identified here is the direction of convectional current, which means that electrons will be flowing from will drift from B to A. So if electrons drift from B to A, already this should give you a hint. If electrons are drifting from B to A, what then would be the polarity of A? Unmute. I would want to hear you.
It's positives.
Electrons are drifting from B to A.
How electrons are drifting from B to A, but the current is moving towards A.
Okay, remember that this is convectional current. Convectional current is flowing from B to A, and electrons move in an opposite direction to convectional current. So current is flowing from A to B, and electrons are flowing from B to A. Do you get it?
I think Punzima get it. Can she answer there and explain?
No, I've already answered. I'm just checking if you understand what I'm what we're discussing.
Yeah, I understand, sir. I understand.
Are you sure, or you're now just agreeing for? So listen, convectional current flows from positive terminal to the negative terminal, right? Then electrons, if you are to determine the direction of movement of electrons oppose the direction of flow of convectional current.
Oh, okay.
So just think of just a simple circuit, like even the one that we have there on the question. our current is flowing from the positive terminal, moving in an anti-clockwise direction. Our electrons will be opposing, moving from the negative terminal to the positive, okay? So now, if you look at our question, we've used our right-hand grip rule to determine the direction of convectional current, and we can see that our current flows from A to B. We do agree that we've used our right-hand grip rule. So now we're saying if current is flowing from A to B, then what would be the direction of the electrons? The electrons will be drifting from B to A. Therefore, what will be the polarity of A?
Okay, yeah, I understand very well.
So the polarity of A will be negative because the electrons are going to accumulate at A. Okay, I hope that is making sense. So you really need this question to... So next part says, once the flux is increased to maximum, what is the magnitude of the induced EMF in the right loop? So we now need the magnitude of the induced EMF. And remember, EMF induced is equal to a negative N change in flux phi over dt. And we have been given, so we're being asked to find the magnitude, so we can ignore the negative. So change in flux is going to be final flux minus the initial flux over the time. And what is our final flux? Our final flux, so I should factor out N there. We're told that we've got 6 turns. Our final flux were given there. It's 6 times 10 to the negative 8. And our initial flux is 0. Because initially the flux was 0. Over the time, which is 100 microseconds, right? I'll just check. We're given, yeah, from 0 to 100, no, 1 microsecond. So that's 1 times 10 to the negative 6. So we can punch that. Six times 10 to the power of negative 8 over 1 times 10 to the power of negative 6. I think I made a typo there. Let me check my flux. That flux is incorrect, right? The flux is 100, not 6. So where I put 6 there, it should be 100. Okay. So if you're punching along with me, you should get 6 volts. We're ignoring the negative because the question is asking for the magnitude. Are we happy with that one?
Yes, sir.
Now let's move on again to the discussions one. Says once the current through the left loop stabilizes, the flux through the loops remain constant. Now, how much EMF is induced in the right loop? So listen to that carefully. Once the current in the left-hand loop stabilizes, the flux through the loops remains a constant. Now, how much EMF is induced in the right-hand loop? That's for you.
Zero.
Reason?
There's no change in flux.
Yeah, change in flux is there. We've been told that the current is stabilized. So if current is stabilized, then flux is not changing. And when flux is not changing, then EMF is there's no EMF induced. Right. Let's move on. Now the switch is opened and the current in the left-hand loop decreases steadily in 0.1 microseconds. During this time, what is the magnitude of the induced EMF in the right-hand loop? So we're simply doing the same calculation again. So it's going to be E is equals to N phi over to T. Okay. Now the loop is being opened. So our number of turns, 6, you multiply by your flux, reaches the maximum flux which were given. Now what changed was the time, which is 0.1 times 10 to the negative 6. So the time has shortened, which means we expect a larger EMF being induced. So this is 0.1. So which means the EMF induced in this time will be 60 volts.
Sorry, sir. The screen is still on that last question. But you can see it.
Oh, you can see it now. So what did you miss?
Yeah, now I see.
So it's simply now the reverse. Now the current is going to be decreasing when you open the loop, and the current is going to decrease, which means that the flux is going to change because current is decreasing. So the flux is going to be decreasing from a maximum to a 0. But the difference is that in this case, the time has shortened. And if the time is shortened, then it means that the EMF would increase, because you can see that there's an inverse relationship between the time taken, because EMF induced is directly proportional to the rate of flux linkage. So are you okay with that?
Yes, sir.
Now let's move on to the theory question again. It says, just right after the switch is opened, what is the direction of the induced magnetic field in the right coil? So we go back to our circuit again. So this was when the switch was closed. Now when the switch is opened, what is happening to the flux?
It's to the left.
Okay. Prince says to the left. How about Mpunzima? What you think? Look at it carefully and check what the question says. Right after the switch is opened, what is the direction of the induced magnetic field? So you can look at the initial scenario that we had. When the switch was being closed, the flux was increasing. Okay.
Which the induced one of in the right coil.
Yes, the question is asking for the right coil. I just wanted to explain something, just maybe it would help you in choosing your answer. I was saying that in the first scenario that we had, we were closing the circuit and current was increasing, which means flux was increasing. Now, in the second question, now the current is going to be decreasing, which means that flux is going to be decreasing. So if flux is decreasing, what happens to the direction of the induced magnetic field? We did discuss about this in the earlier question that we did. What happens to the direction of the induced magnetic field? What happens to the direction of the induced magnetic field when flux is decreasing? What happens to its direction?
Oh, it acts in the opposite direction.
It acts in the opposite direction of the original magnetic field. Okay? So which means that did I say opposite? It acts in the same direction. So same direction as the induced magnetic field. Okay? We have been explaining this from the previous question. Whenever the original flux is decreasing, then it means that the induced magnetic field would be in the same direction. If the flux is increasing, then the induced magnetic field will be in the opposite. If the flux is decreasing, the induced magnetic field will be in the same direction as the original magnetic field. So it's going to be left to right. Now let's try and answer the next one. During this time, right after the switch is open, what is the polarity of terminal A on the right coil? What will be the polarity of A on the right coil? What will be the polarity of A on the right coil? Which means now we have to delete all these directions that I put. Okay. Why? Because the direction of the induced magnetic field has changed. So it's obvious that there has to be a reverse. Okay. But also you should know how to do it. Okay. So it's now going to be a reverse of what we had earlier on because the direction of the induced magnetic field has reversed. So again, we said we use our right hand grip rule. Your thumb will point towards the direction of flow of current. Okay. Then make sure you are gripping the solenoid there. All right. So which means that your four fingers have got your current flowing in an opposite direction of what we had earlier on. So therefore, what would be the polarity of A, if I'm to ask? what would be the polarity of A?
Positive.
Yeah, to be positive, because look, now our current is flowing from B to A. Okay? Current is flowing from B to A. It's B to A, which means our electrons are going to be drifting from A to B, which means B is going to be positive. I mean, B is going to be negative because that's where the electrons are going, and leaving A to be positive. I hope you are following. A will be positive this time. So, then the next question, next part rather. During this time, right after the switch is open, what is the polarity of terminal B on the coil on the right? We've already answered this one. B is going to be negative, right? If A is positive, then B is negative. Well, they can't both be positive. They can't both be negative. And then finally to that one, just right after the switch is opened, what is the direction of the induced magnetic field in the coil on the right? What will be the answer to that? Do you see that this question is a repetition of what we had earlier? Just right after the switch is opened, what is the direction of the induced magnetic field in the coil on the right? So it's a repetition there. So still from left to right. Right. Okay, so check. They're saying our answer here is for B, we said negative, and it's marking it wrong, but it's actually correct. If you then look at the answer here, it says what polarity of terminal B on the right? It's negative. So our answer is correct. Don't be surprised by that. I think it's just a way how the question was programmed. So it marked negative wrong instead of correct, but the answer is actually negative, as you can see there. So I'll advise you to go through this question. It will help you to understand the principle of electromagnetic induction when you have such scenarios. I'll encourage you to go through this question again. Try it on your own and see if you are able to determine the answers that we just discussed here. Okay, it will help you conceptualize that. Let's move on to the next question. Another interesting question here comes. Maybe you've done this question in class. Please read it through. That's question 12. Please read through. I'm just going to be sketching.
The screen says still showing that last
Pardon?
slide. The screen is still showing that last slide. Doesn't change.
Okay, so you couldn't see the question.
Yes, sir, I can see.
So please read through the question, then we'll discuss. If you understood the previous question, then this one should also be simpler now. Okay, I believe you've read through. So in the following schematics, consider that the larger coil is stationary, which is the coil on the left, and is connected to a DC voltage source. The idea is to induce an EMF on the small coil as a result of its motion such that terminal A is positive and terminal B is negative. Which of the following is or are, oh, that's not grammatically correct. Which of the following can be achieve this outcome? Okay, so we need to choose from the three scenarios. So we start with case one. So we want to achieve an outcome of such that terminal A is positive, such that A is positive and B is negative. So this is what we want to achieve. So I made a mistake there. Right. So now this is what we want to achieve. So the first scenario says the positive terminal of the voltage source is connected to D and the small coil is moving to the right. Okay. So which means that D is positive and C is negative. So if they've given us the direction, so which means that they've given us the direction of flow of current. So which means that if you follow the coil, which means that our current will be like that, like that. Now, just to check that you guys are following what we did in the previous question, now that we have identified our direction of current on the solenoid, can you please tell me the direction of the magnetic field on the loop on the left? What will be the direction of the magnetic field there?
To the left, sir.
To the left. Okay. Are you sure you used your right hand grip?
Wait.
Make sure that the solenoid should be in your palm, inside your hand, and your four fingers should align in that direction of flow of current.
Yeah, it's left to right. I don't know what I was thinking. It's left to right. I just did it. I'm sure left to right. Left to right.
Left to right, right? I hope Bunzima also agrees with us. So our magnetic field, which is our original magnetic field, is to the right. So we're told that the small coil is moved to the right. So if the small coil is moved to the right, what is happening to the magnetic flux there? Can you see the small coil? This is the small coil. It's being pushed to the right. Remember, for now you've produced a magnetic flux, but you don't know whether this flux is increasing or decreasing, right? Now they are telling you that the coil on the right is moving further away. So if it is moving further away, what can we say about the magnetic flux induced in that coil? Is it going to be increasing or decreasing?
So could it be that the A will be a positive terminal which will repel the positive terminal of the left coil.
Okay,
'Cause
but we're not yet there. We're not yet there. I want to take you step by step. I want to take you step by step. Listen to my question. My question is, the question actually says we want to induce a magnetic field in the coil on the right. And remember, to induce a magnetic field, we should have a changing magnetic flux. Right? Now, we are flowing a current on the larger coil on the left, and we're going to produce a magnetic flux. And this flux is going to reach the small coil. And we're told that this small coil is moving away to the right. Then my question is, what is happening to the flux in the coil on the left, on the right? Is it going to be increasing or decreasing?
increasing, because it just started changing because of the left solenoid.
Okay, let's
Then
see
the
what
induced.
let's hear what Mponzima is saying. What do you think? Is she still in?
I think it's when it's moving away.
Please repeat. I did not get that.
I think so it's going to decrease when it is moving away.
You think it's going to decrease? I think so too, because look, Prince. We have got a current flowing in the larger coil, and you've got a magnetic field like this. This is magnetic field, right? If you move this coil, the small coil, to the right, what happens to the flux linkage there? Are you going to still be linking many coils, or the flux will decrease if you move it away?
Or as the solenoid on the right decrease, the distance from the left one increase.
Yes.
As the distance increase, yeah, the flux will get weak.
Yeah, the flux will get weak. Okay.
Yeah, will decrease. Yeah.
So now
Yeah.
that
So
we've identified that the flux induced is going to, the flux is going to decrease. Now let's determine what will be the direction of the induced flux. What will be the direction? It's decreasing. What will be its direction? Now you should be quick. You should be quick now. You should be quick. Because we've been doing, when induced flux is decreasing, what would be its direction?
in also to the right, it will be the
Yeah,
same direction as
yeah,
the left.
same direction as the original, right? Now you're getting it. Now you're getting it. So now that we have identified the direction of the induced magnetic field, now let's use that direction to determine the direction of flow of current in the small coil. Remember, we have to grip in such a way that our thumb should point towards the right. We should grip in such a way that our thumb points to the right. So you realize that if you grip properly, then it should be like this, which means our current is flowing from, what have I done? The B is incorrect. Did you manage to grip that correctly? So if you do that correctly, then your current is flowing from B to A, which means your electrons are drifting from A to B. And if your electrons are leaving A, it means they are leaving A to be positive. Loss of electrons attain a positive charge. Do you agree?
Yes, sir.
Yes, sir.
Which means case 1 is fine. So we are fine with case 1. Okay, so I'm not going to draw another diagram. I'm going to erase the directions. And let's do case 2. So I'm just going to scroll so that you read case 2. There is case 2 you can read through. While I'm erasing this. Right, what is case 2 saying? So you see that there is no 2 there, but there's a second 1, which is our case 2. It says the positive terminal of the voltage source is connected to C, and the small coil is moved to the left. Now the small coil is moved to the left. So this coil is moved to the left. And then positive is C and D is negative. So if positive is C, which means our current is flowing like that, goes under, like that, comes to D. Okay, so now the direction of flow of current has reversed from what we had earlier on. Then obviously we expect the direction of the original magnetic field also to reverse, but you should also be able to determine the direction. Means if you grip your right hand in the direction of the current shown, then your north pole would be on the left. Okay, so which means your current would your induced magnetic field would be on the left. That's your B. Okay, and now what happens to the induced magnetic field? Now we have got the left coil moving towards. So if the left coil is moving towards, what do we expect the direction of the induced magnetic field to be? It's moving towards. Pardon?
Opposite.
We expect it to be opposite because the flux is going to increase, because the left coil is going to move closer and closer, which means flux would increase. And if flux is increasing, then the induced magnetic field should be opposing. So which means it's going to be like that, and like that. So again, we've got the induced magnetic field in the same direction as the one that we had previously in the previous question. So if you use your right hand grip rule appropriately, you would realize that your current would move in this direction, which is what we had earlier on. Okay, which means that if current is flowing from B to A, it means electrons are drifting from A to B. And if electrons are leaving A, then it means that they leave a positive charge at A and giving a negative charge at B. So which means that case 2 is also similar to what we have, and that is exactly what we want. Then let's do case 3. So is You can read through while I erase. Case 3 says the positive terminal of the voltage source is connected to D. So which means that the positive is connected to D, is negative, and the small coil is moving to the left. Small coil is moving to the left. So if you identify the directional flow of current, that if you grip that point, realize that your B original is going to the right. So that's your B original. And because it's moving towards, which means flux is increasing. And if your flux is increasing, we oppose. Okay. That's your B induced. So now if your B induced is in that direction, which is the opposite of the two scenarios that we had, then obviously we know that it's going to be reversed. So now if you grip to determine the directional flow of current, either of magnetic field, so which means your current is flowing from A to B, then it means your electrons are flowing from B to A. So which means that in case 3, B is the one that is positive and A is negative because electrons are moving towards A. And this is not what the question is required. Are you happy with that?
Yes, sir.
So only case 1 and 2. Only case 1 and 2. All right, then question 13. So I just left with 2 more questions. Okay, 1 more question to go over. It says, as shown below, the loop of wire side moves through a uniform magnetic field B perpendicular to the page at constant velocity directed towards the right. Which statement regarding electric field induced in the wires is correct for the wires at the right and left side of the loop as soon as the loop leaves the region? Okay, so almost similar to the one that we had earlier on. So this is what we have. Okay, so it says as soon as it leaves. So if you have got a case like that, one side is still in, the other one is it's out, and it's moving. Okay. So you can then use, because first and foremost, we want to identify the direction of flow of current. So we've got the left side and the right side. So the left side is still inside the inside the magnetic field, and it's still cutting across the magnetic field, and therefore we expect to induce a current to flow, okay, because there is a change in flux, okay. Now, I prefer using the right-hand grip rule because that's what I find simpler to determine the direction of the induced current on the conductor on the left. So you've got your magnetic field pointing outwards. If you've got your magnetic field pointing towards you, the first finger magnetic field using your right-hand grip, Fleming's left-hand rule. The field is pointing out, and you've got the thumb pointing to the right, which is the force. Then if I do this, I'll realize that the current is actually flowing downwards. Is it downwards or upwards? Can try and do it. What will be the direction of the current there?
It will be counterclockwise.
Excuse me, not clockwise.
Not clockwise.
So okay. So on the left-hand side, we expect the current to go downwards, right? Am I right?
Yes, sir.
Like this.
On the left side, it will be going down.
Yeah, going down on the left side. Yeah. And then that's the direction of flow of current, right? Then it means that our electrons actually will be flowing in which direction? Opposing. So if you look at the side on the left there, our electrons will actually be moving upwards, right? Because this is convectional current that we used, okay? So our electrons will be moving upwards, and on this side, our electrons are moving downwards. Do you agree?
Yes, sir.
So which means which side is on the positive and which side is on the negative, which means that if electrons are moving upwards, which means that this top side becomes positive, okay? And this becomes negative. And for the side on the right, this becomes the opposite, which is negative, 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 and positive, 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 like that. So let's check the options that we have. They're asking about the electric field. So having done that, then should be. So A says the electric field is directed downwards, in both the right and the left side. That's not true. There's no electric field present in any side of the loop. That's not true. This will be true if the coil was entirely inside or entirely outside. C, the electric field is directed upwards on the right side, and downwards on the left side of the loop. I think that's what we have, right? Is it, or is the opposite? So electric field is always from positive to negative, remember. Electric field, right? So which option do we go for there? Which one is the correct option?
Sir, I couldn't hear you. What was your question?
The question is asking us to find the direction of the electric field. From what we've sketched there, from what our sketch is showing there.
Oh, the electric field will be, I think, different in both sides. For
Yeah.
the left side, it will be going up, and on the right side, it will be going down.
Remember, electric field always from positive to negative. So first you identified your positive, which is your top. So electric field like that. Then here, from electric field always from positive to negative. So it's downwards on the left side. There we are. Question 14, which is the last question for the day. Okay, so I hope you have read through. I'm going to be putting up a sketch there. All right, there we are. I don't know if you were able to see the question clearly. So it says a loop of wire in the shape of a rectangle with width W and length L and a long straight wire carrying a current I lie on a tabletop as shown in the figure below. Suppose the current is changing with time. So your I is equal to A plus BT. So if current is changing, now you know that the magnetic flux around is also going to be changing, where A and B are constants. Now let's scroll down. Okay, so the question says, show that the expression for the EMF that is induced in the loop is given by. Okay, so that's what we want to show. Okay, so question we should ask yourself, are we going to induce a current in that loop? The short answer to that question is yes, we are going to induce a current in that loop. Why? Because we have got a current carrying conductor which is carrying a current carrying conductor. We have got a current flowing and the magnitude of the current is increasing or it's changing. And if its magnitude is changing, which means that the magnetic field around that conductor is also going to be changing, and a changing magnetic field results in an induced magnetic field in the coil, and that induced magnetic field will result in an induced current in the loop. So yes, we're going to induce a current in the loop. So first we have to derive or show that expression in that form. So let's remember, for a straight conductor, that B, or the magnetic field, is equals to mu naught I. By now you should be knowing this. We did this in the previous week, right? And to know the flux, it will be the integral of d phi, because the integral will be, the flux will be a summation, okay, which is the integral of B dA, which is equal to which will be equals to B is a constant, so we can take it out, take that B out of the integral, so it becomes B dA, right? So this can be equal to B, which is equal to mu naught I L over 2 pi integral of the radius, right, over the radius, over the entire radius. I hope you still remember this from the previous so this is just mu naught over 2 pi, because the distance is changing. That's why I factor out that, so integrate dr over r. And here we've got limits from the lower limit, which is h to h plus w, okay? Now, if you recall, u naught I L over 2 pi is the same as 1 over r dr, okay? And this is just basically the same as ln u naught I L over 2 pi ln of r, from a lower limit of h to h plus w, okay? And again, okay, so that means our phi, so it's going to be upper limit minus lower limit, right? That's mu naught I L over 2 pi ln upper limit minus lower limit, which is h plus w over h. So we've substituted in place of r. Okay, then what do we do after that? And remember, this is phi, but we're looking for EMF, right? So remember, EMF E is equals to negative n d phi over dt. And we have got phi, okay? So now we have to differentiate that. So which means our EMF E is going to be equals to negative N, we've only have got one loop, so E is equals to negative. In place of that, we put our D over dt, and in place of phi, we put this mu naught IL over 2 pi ln H plus W over H. We close that. Okay. Then simplify that. This will be equals to negative. You can take that di, because what is changing in all this function is the current. So remember, what is changing in this function is current. So that's what you're going to differentiate. So that becomes mu naught L over 2 pi ln H plus W over H di over dt, because that is what is changing. Okay. Then remember, our I is equals to, I have it here. Our I is equals to A plus BT. A plus BT. So which means if you differentiate di over dt is equals to B. So in place of di over dt, you're going to put your B, right? So which means that your EMF induced E is going to be equals to negative mu naught L over 2 pi ln H plus W over H. In place of di over dt, we put B. Okay. Then, yes, our equation looks exactly what we are being asked to find there. So that's how you would go about that. So as shown in the equation, now the important thing again, what is the direction of the induced current in the rectangle? Okay, I'll choose this. Would you please determine for me the direction of the induced current in the rectangle? You can use the sketch that I've shown, that I've drawn for you here. What would be the direction of the induced current in the rectangular coil?
Counterclockwise.
And if I might ask, how did you determine?
Using if you look at the wire,
Yes.
the current of it is going up,
Mm.
and it will induce the current. It will induce in the loop will be in the opposite direction, which will be counterclockwise.
So first and foremost, I think you need to take it step by step. I don't know how you're having that shortcut. First and foremost, you have got your current. Determine the direction of the magnetic field due to that straight wire. Okay? Determine the direction of the magnetic field due to that straight conductor. Do you get me?
Okay, yeah, yes.
If you use your right hand grip rule, what will be the direction of the magnetic field inside the rectangular coil? So you can grip that coil, that straight conductor, grip it like this with your thumb pointing upwards.
Yeah, on the right side, the magnetic field will be into the page.
Yes. So it will be like this, right? Now, again, now we are focusing with what is happening inside, and you forget about the outside here, right? This is the original magnetic field, B, original magnetic field due to the straight conductor, all right? Then we ask ourselves to induce a magnetic field. The original magnetic field should be changing, and we did realize that it's going to be increasing, right? Yes, with time. So definitely as time increases, then that current is expected to increase, right? So B naught is increasing, which means the flux is increasing. Do you agree?
Yes, sir, but I have a question, sir.
Yes.
Why is the magnetic field for the loop into the page, like inside? Why didn't you mark out the direction for the magnetic field on the left side, saying it's into the page?
Okay, so the magnetic field that I've plotted here, it's the magnetic field due to this straight conductor. We did agree that it's going to be... We did agree that it's going to be like this, right?
Yes.
It is going to be like this.
Or everywhere on the right side, it will be into the page. Okay.
Yeah, of
Okay,
course,
sir, I
of course.
understand.
On the left side of the conductor, because remember it's a circle, it moves like this. Okay, start there, then obviously for it has to come out, into, out, into, out. So that's how it is like. So this is the magnetic field due to that straight conductor. But the reason why I erased, when you are now looking at induced current in the coil, you consider the magnetic field due to the straight conductor, which is in the coil. Did you get that part?
Yes.
So that's why I erased here, because we have to focus on the magnetic field which is inside the rectangular coil, not outside. So in simple term, you can say the magnetic field that is inside the coil is the one that is responsible for the induced magnetic field in the rectangular coil. So we're saying that B original is going to be increasing due to this equation, because as time increases, current is increasing, and as current increases, the magnetic field strength increases. So what does that mean? It means that BI, the induced, will be in which direction? What will be the direction of BI induced?
So you said the magnetic field for the wire is increasing.
Yes,
Yeah.
the magnetic field strength of the straight conductor is increasing. Why? Because current is
Okay.
increasing. And because current is increasing, the magnetic field strength is increasing. Therefore, flux is increasing.
And the induced magnetic field for the loop,
Yeah.
it will be everywhere, not maybe on the right side or it
Inside,
will be
inside,
everywhere.
inside
Everywhere
the loop,
it will be
inside the loop, inside the loop. Remember, you are
inside the
focusing
loop.
on the inside of the loop. And we've realized that the magnetic field due to the straight conductor is into the page. And the magnetic field is increasing. And I'm asking what would be
Oh,
the
yeah.
direction of the induced?
it will be out of the page.
Thank you. So BI will be out of the page, just here next there. That's your BI. Okay. Now use your BI to then determine the direction of the induced current. Now that you've got your magnetic field, now determine the direction of the induced current.
Okay, using your right hand rule,
Right-hand
the
grip rule.
current,
Yeah.
yeah, the current on the left side will be going up.
Are you using your right hand? And are you gripping? Did you
Wait.
grip the conductor on the left hand? Make sure you grip
Oh,
it.
out of the page. I just did a mistake.
Yeah.
It was into the page, man. I didn't curl my fingers in the right
Yeah.
direction.
Yeah.
Curl my fingers towards me.
Yeah.
Towards me.
Yeah.
The my finger will be pointing down, and the current will be going down.
On the left side, right?
Yes, sir, on the left side.
Which means the right side is going up. So which means eventually that's a counter-clockwise direction. Okay? Which means that's a counter-clockwise direction. Did you follow that? Is Mponzima still in?
Yes, I'm still in.
Did you manage to follow what we were just doing there?
Yes.
Then I'm glad. Then you guys, you must be sharp in getting ready for the test. And believe you me, what we've done in this tutorial, one way or the other, the concept will be in the test. So do make sure that you practice similar questions. If you want to still understand more, go through the questions that we've done and see if you're able to work out the direction of the induced current. And don't forget that when the flux is increasing, according to Lenz's law, the induced magnetic flux should be opposing, and if the flux was decreasing, then it should act in the same direction. Those things should help you as you prepare for the test. So these are the questions that I had for today in this tutorial. I hope that this will add to your learning.
Yeah, yes, that it was helpful. We are armed right now, armed
Yeah,
for the test.
yeah, you have to make sure. You have to make sure. So all the best, guys. Join again in the next tutorial tomorrow for the last remaining questions on this topic. So all the best. That is what I had for you guys today. So for me and everyone else, it's a goodbye.